So I hope everyone has go through the lectures on the Stokes theorem, and today I'm going to give you another example of the usage of Stokes theorem. Before that, if you have not looked into the previous 4 lectures, then I advise you to do so. So now let's come to our these new examples where the questions are as written here. They want you to evaluate this term, which is a double integral of the curl of the vector v dot n and over a surface area. And here the vector v is given by this equation yi plus 2j, and you want to evaluate this on a triangle which is made up of three surface. That is this equation of plane, which is 2x plus 3y plus 4z equals to 12, and you have the xz plane and the yz plane. So now in order to have an idea of what it looks like, so you want to plot this on the xyz coordinate, and we choose the xyz axis. So for example, you put x equals to 0. So when x is equals to 0 and y is equals to 0, you have 4z equals to 12, and therefore z equals to 3. So z equals to 3, I have put the point here. And now you do the same. For example, x equals to 0, z equals to 0, and you have to find y. So now here you have y equals to 4. Do the same for the x, and you will get x equals to 6. So you will see that this is my kind of like a surface made up of this equation of plane. And then your xz axis is this one, and your yz axis is the one over here. So now you want to evaluate this term for this surface for this vector field. So what should we do? So here you should recall into mind that this curl of the vector v dot n can be evaluated using the Stokes theorem. And how you want to do this, you have two choices. Alright, whether you want to use the left hand side of the Stokes theorem, or you want to use the right hand side of the Stokes theorem. So let's try with the one on the left hand side first. So on the left hand side, you will have to evaluate this term. You have to look at the curl of the v, and you have to dot with the n, which n is the unit vector normal to the surface. So here you can choose the normal to the surface area to be on the xy plane. So this is my xy plane, and I want to evaluate the curl of v on this plane. So let's do this first. So curl of v will give me I, j, k, and this is partial derivative of x, y, z, and here this is going to be y 2, 0. So this is going to give me I, this is 0, minus j, and this is going to be 0, 0, plus k, and this is going to be minus 1. Okay, and therefore this is going to give me negative k. Okay, then now we can evaluate, as I mentioned before, the one where my surface area is on the xy plane. So you can just imagine the example that we talked about before, where we have a hemisphere. So we have a hemisphere, and this is on the xy plane, and this is the surface. So in order to evaluate the curl of the vector along this surface, you can also do it by evaluating the one on this surface that bounds this whole hemisphere. Right. So we are going to apply the same concept over here. Okay. So in this case, my surface, or my area that I'm interested in, is basically this one. Okay. Right. So let's just write it here. Dot v is equals to k. minus k. So let's just wrap this so we have more space over here. So now we go to the integral. We have curl dot v, curl of v dot n, this sigma, and this is now equals to minus k. And now we are going to choose my normal vector pointing towards the z direction. So this is going to be k and the sigma, right? And therefore here this is equals to minus 1, the sigma. And this means that I just need to evaluate the area of this triangle. And the area of this triangle is just the half of the square, of the rectangle, sorry. So here you have a rectangle that looks like this. So this is, for example, my y direction, and over here this is going to be my x direction. So this is 6, 0, this is 4, right, and this is 4, and this is the triangle that we want over here. So the area of this triangle is going to be half of 6 times 4, right? So 6 times 4 is 24 over 2, and this is going to be equals to 12. So here this is going to be equals to the negative 12. Right, so this is the answer that we got if you evaluate this integral using the Stokes theorem on the right hand side, right, where you do an integral over the surface. So now let's look on the right, where now you want to evaluate this integral in terms of line integral over a closed loop. So now instead of evaluating over this whole area over here, you want to evaluate instead the one over so this is my hemisphere earlier. So instead of evaluating the area of this of this surface, you want to evaluate now the vector along this closed path, right? So now we'll do this. So here we go to the right hand side, and this is going to be v dot dr. So v dot dr is going to be y dx plus 2 dy. So so there is actually 2 ways to do this. So let's go with the idea that we have in the previous example, where we want to evaluate now the curve or the line from this point to this point to the origin, and then back to this 6, 0, 0. Right. So now we have to evaluate line by line. So it's going to be line 1, line 2, line 3. So let's go and call part A, or part 1. So part A, you're going from 6, 0, 0, which is this point, to 0, 4, 0. So this is going to be, my x is 0, my y is going to be 4, z is going to be 0. So here we are going to have 6. So y, we can do it in a better way. So now let's say we have a line like this. So on this line from this point to this point, I will have something like this. So this is my x, this is my y. So this is going to be 4, this is going to be 6. And we want to find the equation of line to represent this path. So this is going to be on this way, right? So the slope of this line is going to be 4 divided by minus 6, and so this is going to be negative 2 over 3. So the line that represents this is going to be y equals to minus 2 over 3x plus 4, right? So you want to be sure that this line is correct. So what you do, you put x equals to 0, and this is y equals to 4. You have this line, and now if your y is equals to 0, right? So you are going to have 2 over 3x equals to 4. That is if y equals to 0, and then your x is going to be equals to 12 divided by 2 equals to 6, and you have this point. So now when we have an equation of line, you will want to find what is dy dx. This is going to be negative 2 over 3 dx. So now we have everything that you need, and you can evaluate this integral. So here you will replace y and dy into this equation, so that now you will have y, this is going to be minus 2 over 3x plus 4 dx, so dx we will retain, plus 2 dy, so dy is going to be negative 2 over 3 dx. And here you will have, let's simplify it, so 2 over 3x plus 4 minus 4 over 3 is whole thing dx. So here this is going to be negative 2 over 3x. This is 4 times 3, this is going to be 12. So this is going to be plus 8 over 3 dx. So now we can evaluate this integral. So this is going to be negative 2 over 3 x squared over 2 plus 8 over 3x, and you're going to evaluate this. This is going from 6 to 0, so this is 6 to 0, and here you will have more space over here, and this is going to be equals to 0 minus, this is minus 6 squared over 3 plus 8 over 3, 6. And now I need more space over here. Yep. So let's just move this over to this side, and we will replace this. So now this is going to be equals to 36 divided by 3 plus this is 3, this is 2, so 8 times 2, this is going to be 16. And this is going to be minus sign. And therefore, this is going to be 12 minus 16, and this is going to be negative 4. So here we have the line integral from here to here, where the answer is equals to negative 4. Okay, so let's retain this somewhere over here. So let's say part A, this is negative 4. So now, next one, we are going to evaluate from this point to the origin. So let's call this as part B, or line B if you want. So this is going to go from 0, 4, 0, which is over here, to the origin, which is 0, 0, 0. And here, if you plot it on the line, on the graph like this, so we can have this as the z plane, and this is z axis, this is the y axis, and here you have just a straight line. So this is 4, this is 0, right? Okay. So this is this part is much easier because you are going to evaluate y dx plus 2 dy. And in this case, my dx is going to be equal to 0 because my x is not going to change because my x is on this line. My x is equal to 0. So here this is going to be 2 dy, and therefore dy I will have y, and my y goes from 4 to 0. So I have 4 to 0 over here, and this is 2 minus 4, and this is going to be negative 8. So part B, this is negative 8. So next, the last one is to evaluate from the origin to this point 6, 0, 0. Okay, so let's go to part C over here. So part C. So part C, we are going to go from 0, 0, 0 to 6, 0, 0. So 0, 0, 0 to 6, 0, 0. And here we can have a graph that looks something like this. So you have x, and this is going to be 6. So here again you have a straight line like this because your point is going from 0, 0, 0 to 6, 0, 0. Okay, so again here y dx plus 2 dy. Now you will see that my y is equal to 0 because I'm along this line, and along this line y is equal to 0. So this term is going to be 0, and dy is going to be 0 as well. So therefore this is 0. Okay, and this means my part C is 0. Therefore I want to take the line integral over this loop. So I have to sum up all the contributions. I will get negative 12. Right. So here what we have done is we have tried both sides of the Stokes theorem. So on the left hand side, I do a integral over the surface, and I choose n as the unit vector perpendicular to this plane on the xy plane. So I'm moving upwards, and I have the answers to be equal to negative 12. And in this case that we have just done, we have evaluated using the right hand side of the Stokes theorem. So I'm evaluating from this 600 to 4040 to the origin and back to this point. So here I'm going to get the same answer as well. And here we can also do it in a different way, which is to take this triangle as the base of the, like what we did for this triangle. So instead of using this area, I'm going to take this area, and we can actually evaluate this point to this point to this point and back. So everything is the same. This is the same. This is not the same, and this is not the same. But then if you do it in this way, you will see that your answers is still the same, right? So maybe you should try to evaluate the line integral for this path. So this point to this point, but then now you go upwards to this point, which is 003, and then go back, and you check whether you should get the same answer as we have done, as what we have obtained before. Okay, so I hope this has been beneficial. If you don't understand, please tell me so that I can give you more examples. Thank you.